So when the wind blows, what kind of energy is that? Yeah, kinetic. All right, the water backed up behind Alcova Dam, what kind of energy is that?
Potential.
Right, so there's the position, and all of our coal, uranium, that's also potential energy. A speeding bullet, a speeding car, or the wind, that's associated with motion. Chemical energy, form of potential energy due to the bonding and type of particles that are there. So you might have heard of a calorie. We'll talk about calories, but we have an international standard unit of energy called the joule, named after James Joule, who demonstrated that energy could be converted from one type to another as long as the total energy was conserved. And we looked at that a little bit on Friday. I said you put gas in your car and all the gas gets burned up, but you wear out the road, you wear out your brakes, you get accelerated and decelerated from point A to point B. That's a force through a distance, so a bunch of work is done. Then you got to buy more gas. Even though energy was conserved, you had it in one nice, useful form, the gasoline. So we're going to look at the joule in a little bit. A second unit of energy is the calorie. That's the amount of energy required to raise 1 gram of water by 1 degree Celsius. Calorie is larger than a joule. A related energy unit is the nutritional or uppercase calorie, which is equivalent to 1,000 little calories. So we don't say kilocalories, we just use uppercase calorie. So if you look at a little bag of Doritos and it says 140 calories, it's uppercase, that's 140,000 thermal calories. So 1 calorie is bigger than a joule. It takes 4 and almost a fifth joules to make a calorie. And 1 nutritional calorie that you might keep track of is that many calories there. So let's ask ourselves the following question. Don't normally spell this out. Kilojoules. So here's the word problem. Only 1 number. That's a good one to start out with. Looks like I'm going to have 3 significant digits to work with. So 1 uppercase calorie is the same thing as 1,000 calories. I'll make the abbreviation there, so nice and proper with canceling all our units. So I want to convert that calorie into joules. So I put calorie down below, joule up top. Look at my unit equation and multiply by this unit factor right here. And everything looks nicely set up and ready to go. 95 times 1,000. Oh yeah, you're right. That is joules. 1 kilojoule, 1,000 joules. All right, 3 digits. Any questions about this process? Candy bar contains 225 calories of nutritional energy. How many joules does it contain? So I write down the given, only 1 number and 1 unit in that word problem. So when I multiply by 1,000, I get to normal calories, because this is an uppercase nutritional calorie. So it looks an awful lot like my first problem there. Pull out your calculator. And joules are kind of small, so we like to work in kilojoules a lot. So when I talk about thermochemistry, my favorite chemical would be water. Liquid water is our product. Ice is our reactant. Is this an endo or exothermic process? Endo. We might think liquid water must have more energy. It's up higher. Liquid, the molecules are free to move around, but they're still touching each other. We say it's a condensed phase, liquid phase, 2 condensed phases. But if we conserve energy, since there's more kinetic energy on this side, we get to write the word heat. And sure enough, it was like 5 degrees when I walked my dog this morning. The heat comes from your drink. Here in a little bit, we're going to see we use Q. So you put the ice in there, it needs heat, it turns to liquid, draws heat from your drink. Well, let's do this. Liquid water going to solid water. Endothermic or exothermic? Absolutely. We can say solid has less kinetic energy than a liquid, more kinetic energy over here. So how do you make ice? Fill up that tray. You're saying, what's a tray? Ice cube tray. And you put it in there, and your heat goes into the freezer, so your fridge kicks on. Now here's my favorite example. Gas going to the liquid, exothermic or endothermic. Yeah, you're going to do the same thing here. Gas has a lot of kinetic energy, liquid has hardly any. So I like to draw this thing that looks kind of like this. Everybody thinks I'm drawing a pig. What am I drawing? Tea kettle. And it's whistling strong, and you put your finger right in there because it looks neat, maybe when you were really young. What happens? If you look at a tea kettle right where it's coming out, you can't see anything, it's clear. So you actually have here, then a little past, you're actually getting little microscopic droplets of water. That's where you see the cloud. Some of this gas condenses into liquid, and where does the heat go? Goes into your finger and gives you a big steam burn. All right, on to the heat and temperature are really two different things. Heat has the units of energy like calories or joules. It's the transfer exchange of thermal energy caused by a temperature difference. And I just went over this. When a piece of ice is dropped into a warm cup of water, heat is transferred from the water to the ice. We say it's an endothermic physical change. And temperature, said this right at the very beginning. When I talked about moving here from a hot area and everybody thought it was hot. Temperature is not a measure of hot or coldness, but it's a measure of thermal energy of matter. I said average kinetic energy, so not the exchange of thermal energy. These are some common misconceptions. Common misconceptions can sometimes show up as a true-false question. So here's the highlight of today's lecture, heat capacity. What is heat capacity? The quantity of heat, we usually use joules, required to change the temperature by a given amount of the substance by 1 degree C. Now, are we dealing with an Olympic-sized swimming pool or a teaspoon of water? We don't know, but a lot of times heat capacity is associated with an object. Now, when we delineate the amount of substance we're talking about and typically use grams, then we are specifying, and so we call it specific heat capacity. And I get real lazy and just say specific heat, the specific heat of water, the specific heat of iron. And I really mean specific heat capacity. And it can be in joules per gram degree C, and we can also have it in Kelvin. So notice we have some interesting units here. I always tell students, fix this up so you can really see what it means. And this here isn't looking that great, and that you really want to realize that the grams and degree C are down in the denominator. Joules are up in the numerator. So it takes like 1/10 of a joule to raise 1 gram of lead by 1 degree C, 0.128. If we go down here and look at water, we say water has a large heat capacity. That makes it a good coolant, in that you got to put a lot of heat into it to raise it by 1 degree C, 4.184 joules per gram per degree C. Where lead here, it only takes 1/10 of a joule to raise it by 1 degree. Here it takes 4. So a big difference there. So here's 1 gram of water, and here I have specific heat now instead of joules per gram degree C, I have calories, and 1 calorie is the same thing as how many joules? 4.184 joules. So when this 1 gram of water absorbs 1 calorie of heat, its temperature changes by 1 degree Celsius. Here this thing's at 20, and I pull out a lighter, Bunsen burner, add 1 calorie of heat, goes from 20 degrees to 21. Now iron here, 0.14, I think on this previous slide it was in joules. Should be almost 4 times that number. Let's just look. Whoops, I'm getting ahead of myself. Yeah, 0.449. And here, when it absorbs 1 calorie of heat, it's going to go from 20 degrees Celsius to 29.3 degrees Celsius. So, reason why water is such a good cooling agent to like run through your radiator. Got to put a lot of heat into it to raise its temperature. So we've already defined specific heat. What we want to see is that it's these 3 components and how things might show up. So here I have a delta T that normally means a change in temperature. And I like to tell students it's like miles per gallon. If you drive 300 miles and that took 10 gallons, what is your miles per gallon? Right, 30 miles and one gallon. So it just looks like 1 degree, but when you do an experiment in the lab, or when you use specific heat, you might get 5 degree change, 23.8 degree change. Same thing with mass. It's implied there's just a coefficient of 1 there and 1 there. But when we work these problems, there's really 3 things we can solve for. We might want to know how much heat. In that case, we take a mass times the temperature change times the specific heat. And we'll see that when we do that, here's specific heat. If I time by mass, and then if I multiply by a temperature change, whatever it is, notice that's going to give me heat. Sometimes you might be given some data where it says a piece of metal absorbs 500 joules, its mass is 30 grams, and the heat changes by 5 degrees. What is the specific heat? And then you just plug everything in, no units cancel, and you calculate a specific heat. Now, math just being what it is, students typically have a more difficult time finding items in the bottom. Like if we want to know mass, and we know the heat, and we know a specific heat, and we know a temperature change, we can solve for mass. Here's my favorite, is if I know a starting temperature, and I know the mass, and I know the specific heat, and a given amount of heat energy is absorbed, I can find a temperature change, and then add that to the initial temperature and get a new final temperature. All these things are dictated by our units. So in ALEKS and in your book, they like to use this formula here. And I said earlier, chemists like to use Q for heat. Of course, M is mass. C is heat capacity, typically specific heat. And then a change in temperature. And so when you have a unit of mass, specific heat was always like joules per gram per degree C. And then we multiply by some degree C. You should see grams canceling, temperature unit canceling, and being left with a heat unit. Q is the amount of heat in joules, M is the mass of the substance in gram, C is the specific heat capacity in joules per gram per degree Celsius, like I got there. The symbol delta means change in, so delta T means the change in temperature. Gallium, interesting metal. I think it's toxic, but it has a low melting point compared to a lot of metals, possibly not mercury, but here it is, melts at 29.9 degrees Celsius. And it says if you hold gallium in your hand, it melts from your body heat. How much heat must 2.5 grams of gallium absorbed in your hand to raise its temperature from 25 degrees Celsius up to its melting point at 29.9. Here's the specific heat of gallium. What are we going to do? Probably the first thing we're going to do is find a temperature change. Should have just listened to the people in the back row. 4.9 degree temperature change. That's our delta T. How much heat? I'm going to look through here, and there's my heat unit. I make sure it's up top in the numerator. All right, here's my 4.9 degrees C. One more thing to multiply by, our mass. Now, it's not exactly in this order. I got C first, and then delta T, and then M. 4.9 times 0.372 times 2.5 There's how we'd want a round to be consistent with our significant figures rules. What is the specific heat of a metal object whose temperature increases by 3 degrees Celsius when 17 grams of metal was heated with 38.5 joules? So this problem might be a little harder than the rest, where you have a specific heat value and you see the units and know where they all go, like a density problem. Is it volume per mass? No, it's mass per volume. But specific heat is what? Amount of heat required to raise 1 gram by 1 degree C. And of course, I always say turn that into a fraction. So now I get to put in the heat unit up top, 38.55. It's a J, thank you. And then 17.5 and our 3 degree interchange. So there we have it, 0.73 joules per gram per degree C. So we want to learn our elemental symbols. Au must be what element? Gold. Suppose it took 108 joules to raise a bar of gold from 25 to 29.7. What is the mass of this gold bar? And we can figure that out if we have the specific heat of gold there. Maybe one little point of bookkeeping before I start. 29.7 minus 25. Might need a change in temperature. Now I see a mass unit right there. So that's where I'm going to start. I'm going to take my specific heat value and turn it into a unit factor. That makes me excited. Unit factors. They come from unit equations. There's my unit of mass. I need to get rid of joules, so I look up here, find 108 joules, and then I need to get rid of, so I took my delta T, my heat, my specific heat value, rearranged it in such a way that I get all my units to cancel. And now I know what to do with my calculator. I know I need to take 108 and divide 4.7 and divide 0.128, roughly 180 grams. It's the mass of this gold bar. All right, have a good rest of your day.